This is an AQA A-level chemistry topic. It's from year 13 and it's transition metals. And this is video number 4 in this series. Going to recommend that you work through this and try the activities for yourself, pausing as you go. And that way you get to see where your strengths are and what might need to have a little bit of time spent on it. So we're going to jump straight in with what you may have done or maybe about to do as a practical. And it's the reduction of ammonium metavanadate using zinc. Now, this is the results table, and ultimately what you need to take away from this practical are the results. That is, what colours would you get and what ion is responsible for those colours. So we're going to look at filling in this table. Remember that we are reducing our vanadium compounds using zinc. So if we're reducing with zinc, that means that our oxidation state of vanadium is going to go down in this practical. So let's work out what the oxidation states are of vanadium in each of the 4 species above. +3 and +2, nice and simple. If I look at VO2+, well, my oxygen is 2- and I need to get to 2+, so that becomes +4. And in VO2+, I've got -4 from the oxygen, so I need to get +5 to get to an overall +1. That means I can put them in order, with VO2 plus at the top down to V2 plus down at the bottom. And I've already worked out the charges, so I can throw those straight in. The question is, do you remember what the colours are for this particular reaction? And I'm going to go through them now. Let's see if you have remembered. VO2 plus would be yellow. That's with an oxidation state of +5. When we go down to +4, the colour is blue. For +3, the colour is green. And for +2, the colour is purple. There is an added confusion here. There is something you may see in the practical. It's something you may be asked about. It's an extra colour. And it's an extra colour that you might see here between the yellow and the blue. What do you think it would be? Well, if I've got yellow and I'm making blue, at some point in between, I'm going to get a hybrid of those two colours, a mixture of yellow and blue. We would also see green there. Now we're going to dig into this a little bit more now. I've already spoken about how we can correctly assign the colours. We know zinc is reducing, so we're going to go from highest oxidation state of vanadium to lowest. But now use this as an opportunity to practice your half equation skills, and in a moment writing or combining half equations to make full equations. When you're ready, see how you've done. So the first one, VO2 plus to VO2 plus, I'm going to start by balancing the oxygens. I need an H2O. I then balance the hydrogens with H plus ions. That's 2H plus on the left. And then I'm going to balance the charge. I've got +4 on the left, and I've got +3 on the left, sorry, and I've got +2 on the right. So I need 1 electron to balance that out. It's now +2 on both sides. If I take a look at the next one, I'm going to start by balancing my oxygens again. So I've got 1 oxygen, I need 1 H2O. My H2O means I need 2 H pluses, and I have now got 4 plus on the left and 3 plus on the right, so I need 1 electron to balance again. Third one, the easiest of the half equations, I'm going from V3 plus to V2 plus. I have no oxygens to balance, I have no hydrogens to balance, I simply need to balance charge, and I do that by adding an electron on the left hand side. And you can see that all of these are reduction. The oxidation state is being reduced for vanadium each time, and we know that zinc is being reduced. So with all of that in mind, now let's have a think about what the oxidation or what the half equation for zinc would look like, and then combining those half equations. Well, zinc is going to go from Zn to Zn plus 2. We need to know that zinc ions are +2. There aren't variable oxidation states for zinc, and they're not variable. We know that because it's not a transition metal. To balance it, I've got +2 on the right, 0 on the left, so I need to add 2 electrons on the right hand side. And now we're going to combine this half equation with the 3 half equations that we just worked with. Now remember, when you combine half equations, you've got to multiply them up to have the same number of electrons in one half equation as you do in the other. There are 2 in the zinc half equation, so I need to multiply this top one by 2. I'm actually going to multiply all of them by 2, so I have 2 electrons in each one. When I combine them, I simply take everything on the left and put it on the left of the equation. So my Zn, my VO2+, my 2H+, and everything on the right of the equation. My Zn plus 2, my VO2+, and my H2O, obviously, with the balancing. So my first equation looks like this. My second equation, we're still going to double this vanadium half equation. And then we combine. And we get 2VO2 plus 4H plus Zn goes to 2V3 plus 2H2O plus Zn2 plus. Finally, I need to double the V3 plus to V2 plus again to get the right number of electrons. 2V3 plus Zn goes to 2V2 plus Zn2 plus. Let's look at a different area where this is important, and we're going to go back to work that you did in year 12, the alcohols topic, and in the year 13 carbonyls topic. So Tollens reagent is a complex, that's now linking it to what we've learnt in the transition metals topic, AgNH3 2+. That actually tells us, because we know that ammonia has no charge, the silver ion here has a charge of +1. Now let's think about how we represented this in year 12 to begin with. I take my ethanol, I add an O in square brackets to represent the oxidizing agent, and I turn it into a carboxylic acid. Now what's actually happening here is the Ag plus in the complex is being reduced to solid Ag. So the observation that we make is that we get a silver mirror forming on the inside of the test tube. It's also important, just as a reminder, that when we do this, Tollens would not work with a ketone because a ketone cannot be oxidized. So I've just added that in as a little bit of extra info. Let's have a think about this now, going back to the beginning of this topic, just as a bit of a review. Why are scandium and zinc not transition metals? First thing to remember about scandium is its only ion is +3. So if I take a look at scandium's electron configuration, if I make a +3 ion, I'm going to lose my 4s2 and my 3d1. I end up with Sc +3 electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6. If I do the same with zinc, Zn plus 2 is its only ion, so my 4s are lost. I end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d10. And that means that both of these do not have an ion with a partially filled d sublevel. And by that definition, by following the definition, they are not transition metals. They're also not going to form compounds with colour, and that is discussed the reasons why in the previous video on colorimetry. Got one final question in this video. So what's the most common stable oxidation state across the transition metals? And by careful consideration of electron configurations, why would this be the case? Well, I'm going to help you out by putting this up. Which is the most common? If you take a look at the transition metals, excluding scandium and zinc, every single one of them forms an ion with a charge of +2. So which electrons are being lost when they become +2 ions? In each case, we are losing the 4s1 and 4s2 electrons. So that takes us to the end of this video. Thank you for listening, and goodbye.